SwayamPrabha. Digital India. Educated India.
Okay, good morning, good afternoon. Welcome back to our series of lectures on analysis and design of rigid pavements. We're actually very far into these lectures. So today we are on lecture 37. We are more than 90% actually done with these lectures. Therefore, it's a good idea for us to just briefly think of where we are overall in the lectures and what we've learned so far. So the lectures were broken up into 4 modules. So module 1 was an introductory module. The main outcome of the introductory module, module 1, was that rigid pavements, there are 4 types of rigid pavements, that's JPCP, JRCP, CRCP and PCP. Of these, mainly in this class, we are interested in JPCP, that's by far the most commonly used type of rigid pavements. We are also interested in CRCP to an extent, although it's much less used, it's not uncommonly used either. JRCP is very, very uncommonly used, so we don't really talk too much about it in this class. And PCP is a relatively specialized application. As of now, it's better learned in structural engineering than in pavement engineering. The second important thing which we got out of module 1 was distresses. So we learned that a distress is anything which causes a decrease in the functional performance of the pavement. And in this case, functional performance, we mean the comfort and the safety of drivers who are using the pavement. So we learned that in JPCP, we are basically interested in 2 types of distresses. There are many distresses, but perhaps the most important ones are faulting as well as fatigue cracking. We are also generally look at IRI, which is not a distress, it's a composite measure of the smoothness of the road, but we are interested in it more for historical reasons. And then for CRCP, we looked at crack width as well as punch outs. There are a couple of other distresses also, but punch outs especially is the main type of distress that we are particularly interested in. Now, module 2 and module 3 was on analysis of rigid pavements. Now, the course is called Analysis and Design of Rigid Pavements, but about half the class was actually set aside for analysis. The reason is that the modern mechanistic empirical design philosophy is actually an iterative design philosophy. That fundamentally means we have to be ready to do a lot of analysis. We have to do analysis multiple times for the same design. So in order to be good at design, we need to be very good at analysis. That's really why we spent about half the class just talking about analysis. So module 3 was on the so-called classical methods of analysis. In the classical methods, the ideas were that under a given set of conditions and a certain set of differential equations which govern the behavior of a rigid pavement or of a dowel, then under a set of assumptions which may not be very reasonable assumptions, but under those set of assumptions, here are some nice closed form solutions. Now, when I say nice, it means that they can be solved by hand, they can be solved by a calculator, maybe you can program a spreadsheet to do it. You don't need any sophisticated computer programming. What I don't mean when I say nice is easy, right? So those equations, Vestergaard's equations and further modifications, for example, those were definitely not easy. And we actually spent a fair amount of time solving some solved examples to show you the many intricacies and the many places where students often make mistakes in calculating those equations. A lot of things to be careful of in those equations. Nonetheless, it's nothing that requires anything beyond basic arithmetic in order to solve those equations. Now, one issue for these closed form solutions or these analytical methods or classical methods is that those assumptions which have been made, they can be fairly unreasonable. Perhaps the most unreasonable assumption or the assumption which causes the most issue is the so-called infinite slab assumption, which is pretty fundamental to a lot of these analysis techniques. So these classical techniques, they make this infinite slab assumption, and we saw through several analyses that the infinite slab assumption can significantly overestimate the stresses. And that's a problem when we want to have a reasonable design. We don't like to overestimate stresses. We like to be fairly accurate in our stress estimation, which brought us to module 3, which is the analysis of rigid pavements using the finite element method. The advantage there was we did not require to make those unnecessary or those sort of limiting assumptions. So those assumptions could be set aside and we could more realistically model a pavement. For example, it could have the exact slab size that we are actually interested in instead of having to forcefully use this infinite slab size. But the downside of it is 2. First of all, in the finite element method, we do not have an accurate solution. So in analytical methods, the idea has been that under some assumptions, we get a solution which does not carry any error. But the assumption in the finite element method is, without having to make those limiting assumptions, we get a solution which inherently contains some error inside of it. So we give up on the idea of getting a very accurate solution. But the way we set up the finite element method is, although we do have an error, we hope, we believe that the error will be small and we can control the amount of error such that it's within some tolerable limit. And indeed, in engineering, we do generally allow some amount of errors, because after all our inputs, whether it's the materials or whether it's the construction, whether it's traffic, everything has some amount of uncertainty associated with it. So we are not really concerned with an extremely accurate solution. Maybe 1 to 2 and maybe 5% error, we are willing to tolerate it, in which case the finite element method becomes quite attractive. The second feature of the finite element method is you need fairly sophisticated mathematics. So what happens in the finite element method is you don't actually have one equation that you have to solve or that you have to evaluate. You actually get tens of thousands, millions of equations that have to be solved at the same time. Obviously, it's not going to be done by hand. Fortunately, there are many commercial as well as open source finite element products available, finite element software available in the market today. So it's not really very difficult. Even without having a very good grasp for the finite element method, it is still possible for you to actually solve problems using the finite element method. That said, FEM is a very broad method. It's not something that was developed for pavement engineering. Particularly if you are civil or mechanical engineers and listening to these lectures, FEM is very, very useful for your application. So in these series of lectures, I tried to give you a brief introduction, a little bit of flavor on the finite element method. There is no way I can cover it in just a handful of lectures. So I do recommend all of you to take a formal class on the finite element method. All right. So that brought us to the end of module 3. So at the end of module 3, we had a good understanding of how to analyze a rigid pavement. When we came to module 4, we were interested in design. Now, the difference between analysis and design, we had talked about this earlier. In analysis, we have everything. We know the materials, we know the thickness of the pavement, we know climate conditions, we know the properties or the other properties, we know traffic, we know everything. We just have to calculate the structural response, which is stresses, strains, or deflections. In design, however, we have none of the above. We don't have a pavement. When we're trying to design a pavement, it means we don't have a pavement. We don't have a thickness. We don't have material properties. We don't have traffic. We don't have climate. We are going to have to make some reasonable assumptions about all of these. And in that process, we come up with something we call a trial section. Then we analyze the trial section. First of all, we calculate the mechanistic responses of the trial section. That is, we calculate the stresses, strains, and deflections. Now, we saw that for pavements, generally we are not considered with one application of a load. We are instead considered with multiple applications of the load, which then brings us to fatigue theory. And then from fatigue theory, we ultimately get the fatigue damage of a pavement. Now, here is when this modern design philosophy can branch off into two directions. We could say that if fatigue damage is less than some value, maybe 1, if fatigue damage is less than 1, then we consider the pavement to be fine, to be okay, to be satisfactory. And if it's more than 1, then we can say that the pavement has failed. That is what you would call a mechanistic perspective on failure. However, the problem with the mechanistic perspective is that fatigue damage doesn't really mean much to a pavement engineer. If I ask you to go out, survey a rigid pavement, and then tell me what is the fatigue damage, you cannot do it. It cannot be measured in the field. Fatigue damage is something that is mathematically calculated using mechanics. It's not directly related to distresses observed in the field. What we can observe in the field, though, is cracking, faulting. We can observe punch outs, we can observe crack width, etc. So these kind of distresses we can observe in the field. That then brings us to the concept of mechanistic empirical design. The idea of mechanistic empirical design is we calculate fatigue damage using mechanics, using fundamental physics. And then the jump from mechanics, so the jump from fatigue damage to cracking or any distress is made through an empirical function, which we call a transfer function. So the idea of mechanistic empirical design is that we use mechanics or mechanistic principles to calculate fatigue damage, and then we use empirical data collected from in-service pavements to convert that fatigue damage into a certain amount of distress. And there are many functions, many empirical functions that allow us to do that. So that was the overall idea, the philosophy of mechanistic empirical design. Now, we have talked about two major implementations of mechanistic empirical design. So again, ME design is a philosophy, And we have looked at two major implementations of these philosophy. The first one, which we have concluded looking at, is the AASHTO Pavement ME, or the AASHTO Mechanistic Empirical Pavement Design Guide. It's largely used in the US and other parts of North America, and it is, I would say, by far probably the most sophisticated and comprehensive implementation of a mechanistic empirical design philosophy for rigid pavements today. It also exists for flexible pavements, but since this class is on rigid pavements, I'm focusing on rigid pavements. So we saw over there in particular that the mechanistic empirical pavement design guide actually uses a particular finite element model to calculate stresses, but actually doesn't even use the finite element model. It actually has developed using the underlying FE model. They've run thousands upon thousands of cases in the 1990s and created a neural network out of it. The reason for that is in mechanistic empirical design, you have to do many computations. You would end up actually having to do hundreds of thousands of computations for a design. That is excessively slow for doing one design. So the idea there was instead of the program having to keep performing finite element analyses over and over again, create a neural network, which is sometimes what we call a surrogate model. So create a smaller model which could quickly give us the answer much faster, something that maybe the orders of thousands of times faster than the full-fledged finite element model. So the mechanistic empirical pavement design guide has actually does 4 neural networks, and we described each of those neural networks in an earlier lecture. So you want to go back and revise that if you need a refresher. So it has 4 neural networks, and using those 4 neural networks, it calculates the stresses. From the stresses, then it goes on to calculate the fatigue damage. And then it uses transfer functions to relate fatigue damage to some type of distress, and that distress can be compared against any policy-driven threshold, and the whole process can repeat. Whether the predicted distress is above the threshold, then we have to go back and change the trial section, which is in design optimization, and we had a complete lecture on design optimization. We also looked at reliability, that is, to what percentage are we willing to allow failure. Generally, for the highways, we're looking at something 90 to 95% reliability, 98% reliability is what we would like, which changes our results. So we looked at all that for AASHTO pavement ME. In the past several lectures, we have been looking at the Indian mechanistic empirical practice, which is IRC 58 2015. Now, IRC 58 is the design guide in India for the code of practice for rigid pavements. It actually, the first edition came out in it in around the 1970s, and currently it's in its 4th revision. So total there have been 5 editions, of which the latest revision right now is what is the legally enforceable version of the code. And this code is built on mechanistic principles. In theory, it is mechanistic empirical principles, but truly it's just built on mechanistic principles. That it's based on the fatigue damage theory. So it does use the concept of fatigue damage, which means it is for a given set of loads, IRC 58 is calculating stresses. When I say IRC 58, I mean the latest edition. So IRC 58 is calculating stresses, and there are many models actually provided to calculate stresses. Of course, it's based on some critical loading conditions. It's based on certain inputs which are provided, for which guidance is provided. And we had a lot of discussion on what those inputs are. For example, climate inputs and traffic inputs. We had a lot of discussion on each of those. Now, today, and then of course what it does is it calculates fatigue damage, and the failure criteria is that the total fatigue damage is less than 1. So it uses a mechanistic failure criteria, which again, as I said, I'm not sure that's entirely a good idea, but that's what it uses. Okay, so today's lecture, so in the previous lecture, I actually showed you first of all what are the critical loading conditions. We'll have a revision of that today. And in today's lecture, I want to show you how you can use IRC 58's critical stress prediction model to calculate the critical stresses as part of an overall design procedure. Now, I should point out over here that there is a companion CD which is provided. So if you actually purchase IRC 58, or more likely if your library purchases IRC 58, they will also get a CD along with it. That CD basically contains an Excel file, and that Excel file has a lot of these prediction models pre-programmed into it. So you don't actually have to do this yourself. Many cases, however, I find that maybe it's not possible to get the CD, maybe the Excel file has some issues with, it might be corrupted or something, many things can happen. And so it's not a bad idea to know how to calculate, how to implement these calculations yourself in Excel. Now, today we are actually going to do the calculations by hand, but I want to strongly emphasize to you that in practice, this must be done in a spreadsheet program. So whether you use Excel or LibreCalc or Google Sheets or any other spreadsheet program, I do recommend that you actually take some time out separately from these lectures. Take some time out and develop your own Excel sheets where a lot of these things have been implemented. in the next lecture, not today's lecture, I will actually show you some results. So one of my students has implemented this into an Excel sheet, and I'll show you some of the results that she has calculated using these models. Anyway, today's lecture though is a very short. It's a very short in terms of its objectives. It's just one objective. The objective is I want to show you how to solve an example of critical stress prediction using the models in IRC 58. Here in particular, I want to emphasize something that I mentioned towards the end of the previous lecture. That is, IRC 58 is fundamentally the stress prediction models. There are two ways to do it. You can have some charts or you have certain regression equations. And the Excel sheets I mentioned actually implement the regression equations. The key thing to understand for those regression equations is they have units. So they have not actually, when they developed these regression equations, they were not non-dimensionalized. And so certain units are still present in a lot of these regression equations. And so it's very important for you as a designer to be cognizant and careful of which units you're using. Previously, when we looked at Westergaard's theory, for example, it was ensured in Westergaard's theory that all the results were independent of the units. That except for one value, which was generally the load, except for one small aspect of it, you just had to make sure that you were unit consistent. And generally there I had told you that you should use loads in newtons and lengths in millimeters. If you do this, use loads in newtons and lengths in millimeters, for Westergaard's theory, you would be fine in using the equations. With the regression equations in IRC 58, however, which I want to show in today's lecture, for these regression equations, however, this is not sufficient. You cannot choose a consistent set of units. Instead, you have to go through the entire description of the equations, and we'll do that today. You need to go through the entire description and check exactly which units are recommended to be used. And you must use exactly those units. In many cases, we end up with mixed units. Sometimes we're using kilonewtons, sometimes we're using newtons, sometimes using millimeters, sometimes we're using meters. We have some degree Celsius and then we have a coefficient which contains some certain units. So we have to be very careful in terms of developing these particular, using these equations, because it's very important to use the correct set of units, not consistent, but the correct set of units. And that's something I want to emphasize in today's lecture. So just as a recollection of what are the critical loading conditions we are analyzing. Broadly, very broadly, there are two types of stress prediction models provided in IRC 58. That is, one is provided for bottom-up cracking, which is the one shown over here, and the other is provided for top-down cracking. Fundamentally, they differ on the fact of where is the critical stress. Is the critical stress in the bottom fiber such that a crack initiates at the bottom and then propagates upward, hence bottom up? Or is the critical stress at the top fiber such that the crack initiates at the top and propagates downwards, hence the name top down? These are two separate conditions which have to be analyzed separately. What we saw is for bottom up cracking, when we have loads, IRC 58 has certain critical loading conditions. The first assumption, the critical loading condition. So if you look at a load, recall from our lecture on traffic, generally we are not interested in cars or bicycles or motorbikes. These lightweight loads we're generally not interested in. It's only buses, trucks and upwards that we consider in our analysis. And in that case, if I try to draw a very cartoonish schematic of a truck, it might look something like this. This is a truck. You can have bigger trucks than this, but this is one type of a truck. Now in this type of a truck, we have a front axle. This front axle is usually of type SASW. That is, it is single axle, single wheel. And the rear axle is almost always dual wheel because it's carrying the heavier load. It could be single axle, so it could be single axle, it could be tandem axle, it could be a tridem axle, it depends. For bottom-up conditions, the assumption is the load has to be centered longitudinally, that the load has to be placed. So if this is the longitudinal direction, and generally in the longitudinal direction, the assumption is that this slab is 4.5 meters longitudinally and transversely it's 3.5 meters. This is not always the case in practice, but in the code, based on the prediction models provided, this is the only assumption that we are allowed to make, because they haven't provided more prediction models for if you have wider or narrower slabs. Okay, so the idea is for bottom-up cracking, we only consider the rear axis. So in this case, we do not consider the front axle altogether. So for rear axles, we could have single axle, in which case the loading condition would be as shown over here. We could have tandem axle, or we could have tridem axle. So I went through this in the previous lecture, so I won't go through all the details again, but the assumption that they made was they actually ran several finite element simulations with this sort of loading conditions and calculate the critical stresses out of that. Okay. top-down cracking is a bit more complicated. The reason top-down cracking is a bit more complicated, in top-down cracking, you actually the critical condition requires that the loads be placed at the edges of the transverse joint. That is pretty much a necessity in top-down cracking. So now in this case, if this transverse joint, so generally this longitudinal distance, this is going to be 4.5 meters. You're not going to have a situation where, whether it's a tandem axle or tridem axle, that the distance between the wheels is going to be 4.5 meters. In generally, the code assumes the distance is 1.3 meters. It can actually be 1.2, 1.5 to 1.8 meters, depending on whether it's tandem or tridem. You have choices in terms of what it can be. So generally, if we are trying to look at critical loading conditions for top-down cracking, we cannot consider only the rear axles, because we'll never have this type of critical loading condition for the rear axle. Instead, we also considered the front axle. So this is what the critical loading condition for the front axle looks like. For the top-down cracking, the front axle is always placed on one of the transverse joints within a slab, and then the first axle of the rear axle is placed on the other transverse joint, still within the same slab. And the remaining rear axles, that is, so if you have a single axle and you don't have anything else after that, if you have a tandem axle, then the second axle in the tandem axle group. And if you have a tridem axle, the second and third axles in the tridem axle group, those are to be placed in the previous joint. Keep in mind, we generally do have dowels. So we usually have dowel sections, so some amount of load transfer is happening. So the fact that the part of the load has been pushed to the other slab does not mean it's going to have an effect on the current slab. Because of load transfer effects, it will also have somewhat of an effect, and the models do consider that. On the longitudinal side, the assumption is, on the transverse side, the assumption is that the outer axle, the outer wheel of the rear axle is kept exactly at the longitudinal edge. That's an additional assumption which is made. How is that correct, and how is it incorporated into WANDER? How does it consider the fact that the vehicles actually move around on the slab, they don't stay exactly at the joint? We will look at that in the next lecture. For now, I'm just giving you what the critical loading conditions are, regardless of how correct it is or how exactly we can take it account into modeling. So, as I mentioned previously, for these loading conditions, these so-called critical loading conditions, IRC 58 provides us two ways of calculating the critical stresses. One way is using visual interpolation of charts. So what they did is, for a variety of axle, for each of these critical load conditions separately for top down as for bottom up, actually this is only provided for bottom up, but for a variety of conditions, for different amounts of loading, for different axle configurations, for different axle loads, for different temperature differences, for different thicknesses and different K values. So they really varied a lot. They performed a very large number of finite element analyses, and then they simply plotted them on a variety of charts. There were actually approximately 111 charts which are provided. So if you actually have a physical copy of IRC 58, it's actually quite a thick book. And that's because a very large number of pages, I didn't count it, but it would probably be at least 30 to 50 pages, are completely devoted just to having these design charts, which just give you the output of the finite element method. So one way to calculate critical loading conditions is to just find a value from these charts and just interpolate values in between. Another way, which is actually the way which is ideally should be done, is using certain regression equations. So we have, what they've done is they've taken the results, they've plotted them in charts, but they also separately try to develop some regression equations to do these calculations. The advantage of these is, when it comes to charts, it's a very visual approach. People can make errors in that process, and then different people will get different answers. Whereas the advantage of the regression equation is that it's possible to program it into an Excel sheet or any kind of spreadsheet. You can program this directly into a spreadsheet, and once you've done it, you know that it's correct and it can always be used. So indeed, IRC 58, as I said, it comes with a companion. It doesn't come with a companion software. If you actually take the CD contains this particular Excel sheet. And so then in the spreadsheet, you can then do these calculations from there. The developers of IRC 58 have ensured the correctness of that spreadsheet. Although in many cases, again, as I've said in the beginning, I do recommend all of you to develop this on your own, and I'll show you an example of that in the next lecture. One thing to keep in mind, as I said in the beginning, these regression equations, which is what we're going to use in today's lecture also, they do contain mixed units. So you have to be careful. You have to look at what exact units you're going to use and make sure you use only those units. Do not use even a consistent set of units is not correct. You have to use exactly the units that they've provided so that you get the correct answer, or you can be wildly off in your calculations. That said, I am going to show how can you check whether your calculations were correct or not. The code itself provides some ways to check, and there are some logical checks that you can also make. And that's what I want to talk about in today's lecture. So let me do that by solving an example. Given following. Consider a 3.5 by 4.5 meter slab. This is the exact same slab size that IRC 58 has. You do not have the option to vary slab size in IRC 58. You have to use these ones because these stress prediction models are built only on this slab size. Now, this slab is part of a JPCP section. It has the following structure. It has a surface course which is 280 mm thick. Okay, note the units, it's in mm. So it's 280 mm thick. If I write this in meters, I'll show you in a second why I'm writing in meters, but this is 0.28 meters. Generally in practice, when you talk to a practicing engineer, or if you look at a DPR, for example, the thickness of a section is going to be shown in millimeters. That is the general practice. So when we talk about thickness of a section, we use millimeters as a conventional unit. IRC 58, however, requires us to use this H, this thickness. It's required to be used in meters. So this is one immediate point where when you're looking at inputs, as you speak to someone, as you get inputs in a practical project, you will get the thickness in millimeters. You have to check that what units of thickness you're supposed to use in IRC 58. It turns out, as I've shown in a couple of seconds, those units happen to be meters, and so you have to use thickness in meters. Given the subgrade K value is also 50.3 megapascals per meter. Now, if you recall our previous lectures using Westergaard's theory, I had told you that this megapascal per meter is an interesting mixed units. You should not use it ideally. You should convert it into Newton per cubic millimeter and then use this. That's what I said for Westergaard's theory, and we did several examples on that in earlier lectures. Please go back to those lectures if you need a quick revision on it. In IRC 58, however, they do use mixed units. So the unit of K value happens to be megapascals per meter. So you should not perform those conversions. Do not, if you're using the IRC 58 equations, do not convert the K value into a consistent system of units. Stick to megapascals per meter. That is what you're required to use by the code. So here's the question. Now we are given some thickness and we're given some K value. We are not provided any information about any other layers. Now, generally, you will have multiple layers. So obviously, this is somewhat of a simplistic example. I will show you a more sophisticated example in the next lecture in part 2 of this series. But right now, I just want to give you a somewhat simple example to this calculation. So here we basically have a slab on a grade situation. Not very realistic, but it's just to illustrate to you how to use these equations. Now, here is the question. Suppose a truck with rear single axis. So we have a truck and it's got rear single axis. That means it basically looks like this. Rear single axis weighing 160 kilonewtons drives on the slab. We have not been told whether these rear single axes are single wheel or dual wheel. Generally, for a truck, since we have said it's a truck, it's almost always going to be dual wheel. So we can assume that this rear axle is actually going to be single axle. Sorry, let me read this, single axle dual wheel. We can make this assumption without too much trouble. We have to think about the front axle, but let's see whether we need that. The question is, what is the allowable number of repetitions for bottom-up cracking? Straight away, you notice I've said bottom-up cracking. If I said bottom-up cracking, as recall from the beginning of this lecture, you do not need the steering axle when you're considering bottom-up cracking. So the critical loading conditions for bottom-up cracking, if I bring up those figures over here, they do not include the steering axle. And therefore, we don't really need to worry about what is the load of the steering axle. All we have to think about is that the rear axle is a single axle, dual wheel is a good assumption, weighing 160 kilonewtons total. Now, the road is assumed to be near Patna in Bihar. Why is this relevant? I'll show you in a particular minute. It will actually come back in terms of climatic conditions. So we are given the location also that this road is assumed to be near Patna. Assume the following. Assume that you have a tight shoulder. That's one problem that we solve when we have a tight shoulder. And then also assume that you have an untight shoulder. Note again that in IS 58, the terminology is a little bit different. Tight shoulders will be written as tied concrete shoulders. So if you look at the code itself, it always uses this terminology, tied concrete shoulders. And for untied shoulders, it might simply write as non-concrete shoulders or does not contain concrete shoulders. But that's basically it's an untied shoulder. Okay. Now, we are basically being asked to calculate what is the number of allowable repetitions. I should have decided here, this should be number of allowable repetitions. So we are asked to calculate the number of allowable repetitions for this particular condition for bottom-up cracking only for tied shoulders as well as untied shoulders. Okay. To calculate the allowable number of repetitions, obviously we are going to use our SN relationship, our SN curve, which we saw previously, where N is the number of allowable repetitions, that's what we want to calculate, and S is the stress ratio. So if we have a stress ratio, that means we need a stress. So clearly we need to be able to calculate the stress. Therefore, we need to assemble all the inputs we require to calculate stress. Before looking at the equation for calculate stress, one thing, if you recall, which I already showed you, you do require a value of delta T. That's one of the predictive values that goes into it. You have to know what is the delta T value, in this case, for bottom-up cracking. So for that, we have to look at this. This was table 1, if you recall, and I showed you this in an earlier lecture. This was table 1 in IRC 58. We open up this table. It's given that we are near Patna, Bihar. We are given that H is equal to 280 mm. Okay, so let's find Bihar in this list. Bihar is over here. If you look at zone 3, it says Bihar, Jharkhand, West Bengal, Assam and Eastern Orissa, excluding hilly regions and coastal areas. So Patna, I haven't been to Patna, but I'm fairly sure there are no hills over there. So we definitely are not looking at any hilly regions, and it's definitely not, it's a landlocked state, so there's definitely no coast. So it's safe to use zone 3 Bihar for Patna. Now our thickness is given to be 280 mm. If we look at this column over here, what are the thickness values for which we have prescribed values of delta T? We have 250 mm and then we have 300 to 400 mm. Below that we have 200 mm. 280 is somewhere in this range, 250 to 300. For 250, we are given to use delta T of 16.6 degrees Celsius, and then for 300 to 400, we are given 16.8. The actual thickness we are given is 280. So we have two ways to do it. We could do an interpolation in between that. If we know at 250 we have 16.8, and at 300 we have 250 we have 16.6, and at 300 we have 16.8. We can do a linear interpolation and calculate what would the value be at 280 mm. In general, that's not what we do in practice. We just decide to find the nearest value. So 280 is closer to 300 than it is to 250. Or you can say, if you want to be a little bit on the conservative side, let's go to the slightly higher value. And so we end up, the idea is there, use 16.8. So 16.8 is a little bit of a conservative value. If you properly interpolated it, maybe you'd get 16.7. Not going to make too much of a difference. So just to be a little bit more on the conservative side and save ourselves a little bit of calculation, which we don't want to do, let's just take 16.8. So we choose then from this table, delta T is equal to 16.8. Okay, now we have to calculate the stress. If you recall the equations I showed in the previous lecture, the stress regression equations, we're not using the charts yet. I will show you the charts later to verify the results. But just in terms of using the equations, you saw that you have different equations for different K values. So the K value was less than 80 megapascals per meter, you had an equation. If it was between 80 to 150, there's another equation. And if it was greater than 150, there was another equation. So just sticking to K value of less than or equal to 80 megapascals. And so in our case, what we had is K value is 50.3 megapascals per meter, which is less than 80. And therefore, we will pick the corresponding equation. Equations are also provided separately for single axle and tandem axle. Again, this is for bottom up, so we're talking only about rear axles. So we have separate equations for tandem, separate equations for single. Tridem equations are not provided because according to the code, the stress due to the tridem axis is very low. So there are no equations provided for tridem axis. So for single axle, now we can have both tied and untied. So here's the equation for when you have a tied shoulder. You have S, which has this particular functional form. And then you have the single axle without concrete shoulders, which again you have some particular functional form. So it's just an equation. The coefficients have come out of some regression. There's really nothing much to comment about it. You will see here the input. So here you've got gamma. Gamma is the unit weight of concrete. We'll see in a second what value we can use. We have H over here, which is the thickness that we already saw. That's 280 mm. K value is 50.3. We have that. This L over here, in the code, this equation I got exactly from the code, so I just took a screenshot of the code. Here, this L, it's a little bit confusing to read. This is actually this script L as we write. This is the radius of relative stiffness, which we saw way back in the beginning of module 1 from Westergaard's theory. So even here, this radius of relative stiffness has made a very fruitful comeback. Another set of inputs, we have P. P is the load of the axle. So since this equation is for a single axle, P is the total load of the axle. Common mistake. Many students erroneously assume that P is the load of the wheel. It is not the load of the wheel. The way the regression equations have been done is it is the load of the total axle. The assumption is that it is a dual wheel axle, and therefore when developing the finite element equation, they took the total load of the axle, they divided by the number of wheels, assuming that all the wheels carried the same load, and then those were placed accordingly as we described previously in the critical loading conditions. But in developing the regression equations, the input was simply the total load of the axle. So P is the total load of the axle, not the wheel load, and the units are kilonewtons, not newtons, kilonewtons. Anyway, we'll talk about units a little later. HKL we already talked about. Delta T was this value which we just got. For this, these are the equations for bottom-up cracking, another set of equations to use for top-down cracking. Now, let's look at the units. This is a very, very important slide. So I'm going to go through in a little bit of excruciating detail over here because it's the most common error you can make is to use the wrong set of units. So S is the flexural stress in the slab. This is actually the critical tensile flexural stress. Flexural stress can be both compressive and tensile. We are interested in tensile. So this is the critical tensile flexural stress in the slab. It is in megapascals. Keep that in mind. Delta T, this we actually saw previously in our climate lecture. It is the maximum temperature differential in degrees Celsius during daytime for bottom-up cracking. So that's the value we pick up from the table. Well, ideally the code says that you should be getting local values and doing a more detailed analysis. In practice, people use that table, and we talked about the issues with that table before. Please go back to an earlier lecture for a summary. Okay, or it is the sum of the maximum nighttime negative temperature differential and the built-in negative temperature differential for top-down cracking. This value, this built-in temperature differential, this was 5 degrees Celsius, actually minus 5 degrees Celsius, but again, we use the absolute value. So one thing which is not mentioned over here, delta T, use an absolute value, which is if you're calculating for bottom-up cracking, delta T is positive already, so there's nothing much more to do there. But if you are doing the analysis for top-down cracking, then make sure you don't use a negative value of delta T. Use the absolute value of delta T, although in practice you are correct that delta T is negative for top-down cracking. But the code, the way these equations were set up, they were based on the absolute value. So again, common mistake, don't make that mistake. Okay, H is the thickness of the slab in meters. Keep this thing in mind. This is again a common source of error. When we, as I mentioned previously, and it's a very important point, that's why I'm belaboring it a little bit longer. H generally in our regular conversation in a DPR, in practice in civil engineering, thicknesses, whether in slabs, whether in structural engineering, whether in geotechnical engineering, etc., thicknesses of structural elements or members are always shown in millimeters. That's just what our practice is. The regression equations, however, have been developed using meters. If you ask me personally, I think there's a need to go back and make these whole system of equations unit consistent so that these kind of issues with units don't keep coming up and mistakes are not made because of it. But anyway, I'm discussing what we have right now. So the thickness has to be in meters. That's also why in the inputs for this problem, although it was given, it was 280 mm, and that's the correct way to write it. You should express the thickness in millimeters. I did immediately tell you to rewrite it in meters because the inputs need to be right. The H, according to the regression equations, must be in meters. K is the K value again, and here the units are megapascals per meter. So here, coincidentally, this matches what is the system of units, what is the conventional units we use to describe K value. The same conventional units are also used in this in the regression equations. Whereas in Westergaard's equation, we would actually have to convert this into Newton per cubic millimeter in order to be unit consistent. The radius of relative stiffness is the same formula. So again, this is one of the formulas I told all of you to memorize. This is something you should know. I know in this case, we haven't seen the formula for a long time, but I'll just rewrite it for you. It's the fourth root of EH cube into 12K into 1 minus nu square. It's very important here for us to keep in track the unit. So I just said H is in meters. What are the units of E? E is the elastic modulus. Previously, we have been using the elastic modulus. It's always reported in gigapascals. So when you say elastic modulus of concrete, you always report it in gigapascals. That is our engineering convention. Whether it's concrete or steel or whatever material, we report the elastic modulus in gigapascals. However, in this case, the requirement here is the elastic modulus has to be in megapascals. So previously, we have been using a value of E is equal to 30 gigapascals in all our previous calculations. Indeed, even in structural engineering, 25 to 30 gigapascals is what you would use for elastic modulus of concrete also. But keep in mind, you are required here to use it in megapascals. So your value to use should actually be 30,000 megapascals. Do not use the value either in gigapascals or just in pascals. Use 30,000 megapascals. All right. Mu doesn't have any units, so nothing much to think about. Gamma. Gamma is the unit weight of concrete. What is unit weight? Unit weight gamma is basically the density into g, acceleration due to gravity. That's the meaning of unit weight. The density of concrete is generally 2,400 kilograms per cubic meter. It can vary. It can be as low as, for typical concrete, it can be 2,200 to 2,500. If you're using different types of concrete, maybe with steel fiber, maybe you can go above 2,500. If you're using lighter concrete, maybe lightweight aggregates, you might go below 2,200. Somewhere in that range, a decent typical value. If you don't know anything else, a decent typical value is say 2,400, and that's what the code recommends also. Into G. Now, G is technically 9.81. Since we are engineers, we are happy to just write G is equal to 10. So, basically, we have gamma is 2,400 kilogram per cubic meter into 10, which is G, and that gives us 24,000 Newton per cubic meter. But the recommendation for gamma, and this is again an example of mixed units, the recommendation is gamma should be in units of kilonewtons per cubic meter, right? So, although it's 2,400 into 10, that's 24,000 Newton per cubic meter. It is recommended, and there's by the way typo over here, this should be densities in cubic meters. So, it is recommended that the value should be in kilonewtons per cubic meter. So, this is another conversion, unit conversion, which you're going to have to perform on the way. These unit conversions are generally what will trip up students. That's why I'm emphasizing it so strongly. P, as I already mentioned, it is the, for bottom-up cracking analysis, it is the single or tandem axle rear axle load. It is the total axle load, not the wheel load. No fatigue damage is computed for front steering axle for bottom-up cracking. I already mentioned that. Okay. So what we see over here is then in our system of units, we have you have mixed units in these equations. So this slide, which I've taken several minutes to look at, it is very, very important that you remember this slide, that you keep checking this slide when you're developing your when you're doing your calculations, when you're developing your spreadsheet. Do not get the units wrong. If you get the units wrong, then there are ways to figure out that you've made a mistake in a calculation. We'll talk about that as we proceed with this calculation. First thing we have to do, we have to calculate the value of L, the radius of relative stiffness. Note here the radius of relative stiffness, they haven't mentioned what units to use. This is a typo genuinely in the code. The radius of relative stiffness, as the code requires in the regression equations, is in meters. So please note that down. This is something which is missing from the code. The radius of relative stiffness must be in units of meters. That, by the way, is different from what we've been doing in the past. When we were looking at Westergaard theory, we used millimeters for radius of relative stiffness. Now we are saying the answer must be in meters. If you use millimeters, your stress calculations using those regression equations will be wrong. So let's try to plug in a value. So we are given L is 4th root of. Now again, the answer has to be in meters. So we have to be very careful about units. So E is recommended to be in megapascals. So this is going to be 30,000 megapascals, right? So this is going to be in Newton per square millimeter, which is megapascal. H cube, we're given H is 0.28 cube, and the units are cubic meters because H is required to be in meters. So H cube is going to turn into 0.28 cubic meters. You're already seeing a mixed unit issue coming in right here. Okay. 12, we have the 12 into K. K is 50.3, but the units are megapascals per meter, which can be written as Newton per square mm meter. Again, mixed units are being brought in here. Nu fortunately doesn't have any units. Nu is going to be 1 minus. We're not given a value, so we use a typical value 0.15 square. We can do the calculations with the numbers. That's not a big deal. Let's just be very careful of the units. Again, the answer has to be in meters. So what we see here is Newton per mm square and Newton per mm square are in the numerator and denominator. They both cancel out. This meter, which is in the denominator of the denominator, that will then go up to the numerator. So finally, we're going to get this in meter power 4, but we take a 4th root. Again, this is a common mistake by students, forgetting to take the 4th root and taking the square root. It's not a square root, it's a 4th root. So we take the 4th root, and so our final answer is the 4th root of meter power 4. It's going to be in meters. So in this case, we do get the correct system of units, but because the code is so sensitive to units, please make sure that you explicitly check what system of units you're using in your calculations. Very, very easy to make a mistake on this one point. I did the calculation for you, so I'm not going to do the final calculation. Again, I encourage all of you to create a spreadsheet of your own and do this calculation. What we see in this case is L works out to 1.03 meters. Back in Westergaard, we would have written this as 1030 mm. We would have done that over there. In this case, the requirement is just to put it in meters, so it's 1.03 meters. So now we have successfully calculated L. This calculation I already shown the calculation of gamma. So the gamma is basically rho into G. Rho is, we can take 2400. If you don't have the exact mix design, we can just use 2400. This is in kilograms per cubic meter. And then G we can just take as 10, because we're engineers, we are entitled to make these kind of assumptions. So G we take as 10. We get the answer as 24,000 Newton per cubic meters, but it's required to be in kilonewtons per cubic meter. So that's why you must write it as 24. If you use 24,000, you will get a wrong answer on the stress. Again, the system is not unit consistent. There are units which are specified. So it must be in 24 kilonewtons per cubic meter. It must be in kilonewtons per cubic meter. Okay. So finally, here is our formula in all its glory. For this particular condition, for tight shoulders, for a K value which is less than 80 megapascals per meter, for bottom-up cracking, for under those peculiar conditions for single axles, single rear axle, this is the equation that we have. Let's start plugging in our formulas, and here again be very, very mindful of the units. So 0.008, this is a number. Technically it has a unit. The unit is megapascals, because S on the right hand side is in megapascals. This coefficient, this intercept, also has the units of megapascals. Okay, minus 6.12. This also has some particular units. You can figure it out on your own. Gamma has to be 24, because it has to be 24 kilonewtons per cubic meter. H has to be in meters, so it's 0.28 square necessarily. Okay, divided by K is 50.3 megapascals per meter. This one is fine. And then L is 1.03 square meter. This is square meter here. So keep in mind, we do have to, so these square meter cancels. You can check the consistency of the units later. I'll leave it to you to figure that out. But you will see that you should not end up using the wrong units. Do not use 24,000 Newton per cubic meter. In Westergaard's theory, I had said you need to be unit consistent. For IRC 58, I'm telling you, you need to use the units prescribed or specified for the regression, because these coefficients are not unitless. They have a unit, and therefore you have to be careful in terms of what units you're using for the final answer. Okay, if you look at this particular term over here, so this is going to be plus 2.36. P is 160. So if you go back to the problem, let me remind you of this. So it was given the single rear axle weighing 160 kilonewtons. Again, kilonewtons. So P is necessarily going to be 160. It's 160 kilonewton into H, so it's 0.28 meters, divided by K, which is 50.3, same units, into L power 4, so 1.03 power 4 meter power 4. And then delta T, we already saw, we are going to use 16.8 degrees Celsius over here. So the reason I wrote this out in such laborious detail is to warn you to use the correct system of units. Again, I'm repeating for the last time, do not use a consistent system of units in this case, because this is not a non-dimensionalized equation. Instead, this, unlike Westergaard's theory, which was a non-dimensionalized equation, this is a dimensional regression equation. It does contain certain dimensions. In my personal opinion, the next update to this should non-dimensionalize these equations. This dimensionality can be the root cause of a lot of errors. But to avoid that, just be very, very cognizant as of now for what the units are which are being used. Okay. You can do the calculation on your own, and I did it. Again, I encourage you to set up your own spreadsheet and do the calculation. In practice, as practicing engineers, you do have spreadsheets which do these calculations. So you should be very good at setting up these spreadsheets. I did it for you, and you can double check that I put all the units, etc. correctly. We get the final answer of 2.12 megapascals. Is it correct? We'll talk about that a little bit later. This whole example was for tight shoulders. Before we talk about the correctness of the solution, let's just, okay, well, one way to check the correctness, so I move the order of the slides. One way to check the correctness of the solution is to actually go back to these charts which are provided. Now, the chart is not directly applicable. If you look at this particular chart, so what do we have? Again, the charts are only provided for bottom-up cracking. There are no charts provided for top-down cracking. For bottom-up cracking, then we have to look at the caption, and this is chart number 44. This is in, and these charts are provided in Annexure 4 of IRC 58. So if you look at figure 4.44, so figure number 44 in annexure 4, it's quite deep into the annexure. This is stress due to single, this is again all for bottom up cracking. Stress due to single axle load of 160 kilonewtons. That's exactly what we have. Our load is 160 kilonewton, it was single axle. So that tells us we should probably use this. But given delta T is 17. Now, technically we have delta T of 16.8. Besides 17, I believe delta T of maybe 13 is also provided. So you could technically do an interpolation between the two. Generally, we can say, okay, 16.8 and 17 are roughly the same. It's very close to each other. So let's just stick to this value. Again, we are just trying to verify this value. Are we getting almost 2.12? We need not get exactly the same value. With tight concrete shoulders. That's exactly what we did this analysis for. It's with tight concrete shoulders. And so this seems to be the correct figure to use. Now, what is the thickness we have? Our thickness was 280 mm. It's somewhere around here. So our x-axis value has to be over here. What about the K value? Now, K values which are provided over here are 40, 80, 150, 300. None of them are exactly what we want, so we kind of have to visually interpolate. So, for example, we might roughly say, okay, this point corresponds to a K value of 50.3 roughly. It's very rough. Visually interpolate from here, and then we pull it out and we get roughly 2 megapascals. So again, this is very visual, and I hope with this you can see why it's not a good idea to use these charts for the large part. It's fine that they provided them, but in practice you should use the regression equations because there's a lot of subjectivity in using these charts, and depending on the font size and the thickness of the lines, it can be really difficult to use these. So basically what we get here, roughly 2 megapascals roundabout is what we're getting, and our calculation gave us 2.12 megapascals. Reasonably close. It's the error is less than 10% between these two. So, okay, we might say that our calculation here looks okay because the chart we're getting roughly the same values from the charts. Okay. Similarly, we can do the same process for untight shoulders. So for untight shoulders, we have this here, we have S is minus 0.149. You might notice here an interesting thing is these don't look for any patterns in these coefficients because the equations have not been non-dimensionalized. Some coefficients can sometimes be positive and sometimes be negative. You get a variety of different conditions happening. So for tight shoulders, our intercept was positive and small. For untight shoulders, our intercept is actually negative and much larger than that intercept. It happens because this is what happens when you have non-dimensionalized regression equations. So, but here again, the inputs are pretty familiar. So, gamma h square over kl square, we've already seen how to do this. pH over kl power 4, again, I showed how to do this, how to plug them in, be very cognizant of the units. So, I'm not going to repeat it again. Delta T is the previous thing, so 16.8. With that, you get a value of 2.76 megapascals. Like we did last time, we can also look at the corresponding chart. So, this is actually chart number 19 in annexure 4. So, stress is this, again, this is all for bottom up cracking. Stresses due to single axle load of 160 Newton, P is 17, which is close enough for us, but without concrete shoulder. So previously, chart number 44 was with concrete shoulder, tight concrete shoulder, and this is without a concrete shoulder. So here again, 280, K value again doesn't exactly correspond to what we want, so we have to kind of visually guess what we're doing. I tried to roughly do it, and maybe I got something of, this might be like 2.8 megapascals, very roughly speaking. So our regression equation, we got 2.76. Over here, we got 2.8, reasonably close. So most likely, our calculations are correct. We haven't made any unreasonable, we haven't made any unit errors are the most common errors, but we haven't made any errors in this calculation, in this example. So one way we know for bottom-up cracking only, again, top-down cracking, these charts are not provided. For bottom-up cracking, the way we know whether we did it correctly or not is you can just, for a couple of cases, as we'll see in the next lecture, you'll actually have to do the same analysis for many, many cases. So you don't want to keep repeating this. But for a couple of cases, it's good to just check whether you're getting a similar value with the chart that tells you whether you're making any serious errors or not. This is, of course, if you're developing your own spreadsheet, which I do recommend everybody do. If you're using the spreadsheet which has been provided with the IRC code, then you need not do all this because the authors of the code and the spreadsheet have already guaranteed that these are correct. So they've done all these checks already. Okay. Now, one thing I want to check for both cases, suppose we say FCR, which is the flexural strength, suppose it's 4.5 megapascals, a reasonable value. Then if I just calculate stress ratio is this critical tensile stress which we just calculated divided by FCR. For tight shoulders, I get stress ratio of 0.51 and for untied, I get 0.66. Does this seem correct? Okay. This is what a typical thing an engineer would have to do. you're not just calculating numbers, you also have to see whether the numbers seem correct based on what you would expect. So it's a good question. So let's take a minute to try to understand how to answer this question. First of all, we learned, if you go back to our lectures on Westergaard's theory, stress ratio is generally going to be 1. Pavements do not fail instantaneously. Stress ratio is generally going to be significantly less than 1. And in this case, 160 kilonewtons for a single axle is actually a fairly heavy axle. It can get higher, you could have 190, 180, 190 also, but generally this is a pretty heavy axle as it is. So for a fairly heavy axle, we are getting relatively high stress ratios, 0.51, 0.66. They're less than 1, they're quite less than 1, but they're not very small either because the axle is not that light, it's a fairly heavy axle. So these values reasonably look correct in that respect. Furthermore, as we see, for tight shoulder, we get a stress ratio of 0.51, and for untied, we get a stress ratio of 0.66. This is also correct. When we have a tight shoulder, so tight shoulder basically means this is my main travel lane, and then I have a shoulder, and then I have tie bars across the shoulder. So these tie bars are enabling load transfer between my main travel slab as well as the shoulder. And therefore, the stress should decrease on the slab because some load transfer is happening because of the tie bars. Whereas if we have untied, then we don't have this load transfer and the stress in the slab itself should increase. Consequently, the stress ratio should be higher for untied versus tied JPCP. And that's what we get with these calculations. So based on these two, looking at the magnitude of the numbers on their own and looking at the relative value of the two numbers, these answers seem to be reasonable. Now the question asked to calculate the number of allowable repetitions, N or NF, there are different notations for it. This is the equation which is recommended to be used in IRC 58. Again, you can do these calculations. If it's less than 0.45, I reiterate, this is called the endurance limit. If it's less than 0.45, by the way, not all these SN curves have endurance limit. The version being used in the IRC code has it. There are the AASHTO function, the AASHTO endurance limit, the AASHTO SN curve does not have it. And so there are many different types of SN curves. I had given an entire lecture on that. Sometimes you have it, sometimes you don't. The IRC 58 SN curve does have it. So you can do the calculation. So our stress ratios are definitely above 0.45. So we don't have infinite number of repetitions. But for the other two, you can go ahead and do the calculations. In one case, we had 0.51. So that's going to use this one. For the untied one, we had 0.66. So it's going to, by the way, there's a typo over here. This should be greater than 0.55. This is in the code itself. So there's a mistake over here. Please keep that in mind. If you apply the formula, what we'll get is for tight shoulders, we get roughly 370,000 allowable repetitions of this particular axle, that's 160 kilonewton axle, for this particular temperature difference, 16.8 degrees Celsius. And for untied shoulders, we get 14,000. What you'll see is, as we expect, the number of allowable, because the stress ratio is higher for untied, the number of allowable repetitions is lower. You can apply lower repetitions of a higher stress. What you'll see is actually an order of magnitude different. It's very typical. If you look at the equation, these are logarithmic. So algebraic changes in stress ratio, that is, if you make a small change in stress ratio, which is on algebraic orders, 0.1, 0.2, that sort, then you're going to get logarithmic changes in the number of allowable repetitions. That's how the equation is built. So don't be surprised when you see more zeros popping up when you're doing it. Secondly, what you'll see, I have actually rounded off the NF to a round number. This is also fairly common to do. Generally, we get very accurate values. We can get down to decimal places, but we typically in practice, we just round it off to some roundabout values because generally we have enough uncertainty that we don't have to be concerned about the exact value. It's fine if we just round it off. Although in the Excel sheet, you'll get the exact value. As we'll see in the next slide, you just continue to use the exact values. When you're reporting it, it's okay to just round it off. Okay. Now, that's the entire example. If suppose I asked you to do it for top-down cracking, I'm not doing it for top-down cracking, but I'm leaving this to you as an exercise to do on your own. If you had to do this for top-down cracking, what would change? Firstly, for top-down cracking, the temperature difference to be used would be 16.8 divided by 2 plus 5. So that's going to get you 13.4. Do not use the negative sign. Use the absolute value. So if you're using top-down, now you don't use 16.8 as delta T, use 13.4. Secondly, you would use this equation over here for calculating the critical stress. Here, S again is in megapascals. What is interesting to note is you have this term P. The other terms I've defined before. P, for top-down cracking analysis, P is 100% of the rear single axle, 50% of the rear tandem axle, and 33% of the rear tridem axle. So it's basically, if these are the front axles, then if you have single axle, you use all of it. If you have a tandem axle, it's telling you use half. If you have a tridem axle, you use 1/3 as the value of P, right? You can look at the rest of the calculations here, and there is one particular value, B. B is actually the transverse load transfer. So if you have dowel bars, it's a coefficient which is supposed to be 0.66, which assumes 50% load transfer efficiency. This was that terminal load transfer efficiency which I had talked about in the previous lecture. If there are no dowel bars, that is, the load transfer efficiency is taken as 10%, that's generally coming from aggregate interlock, and base friction, then B is recommended to be 0.9. So you have to be careful which value you're using, depending on whether you have dowel bars or not. Okay, I'll leave you to another question. If we have a 240 tandem axle in the rear, the only change to make is you use this value of P, which is the tandem axle. All right. So this example, I'll let you take care of yourself. Note that no charts are provided for top-down cracking. So we can't do that same kind of verification as we did for bottom-up cracking. All right, with that, so I took you through an example to show you how you can use IRC 58, how you can use those equations. I strongly recommend you learn to implement them in a spreadsheet. It's not, from an engineer's perspective, it's not good enough if you're just doing it on a calculator. You should also be able to implement it on a spreadsheet. That was one example for one particular thickness. So it was basically an analysis problem. This is not a design problem. I gave you the thickness. What we will look at in the next lecture, which will be one of the last lectures in IRC 58, we are going to look at how to do a full-fledged design. And there I'll show you an implementation that my student did in Excel, where we did all of these calculations in Excel, and I'll give you some tricks and some ins and outs of doing this calculation. So I'll see you there in the next lecture.